Okay, so we are recording now. I'll just start with a very quick introduction. And I know all of you have the link. So Emily is an associate professor in computer science and engineering and a Toyota faculty scholar at the University of Michigan. She received her doctorate in electrical engineering from the University of Southern California. She's been awarded a National Science Foundation Career Award, the Oscar Stern Award for Depression Research, which is quite interesting to think of a researcher with her background getting a depression research award, and that'll all become relevant in a moment. An NSF Foundation grant research fellowship. She's the co-author on the winner of the best student paper at ACM Multimedia in 2014, a co-author of the winner of the Classifier Sub-Challenge event at the Interspeech 2009 Emotion Challenge. So she is interested in human-centered speech and video processing, which of course is an area that folks at BRiTE are very interested in, and we're all thinking of doing more and more work in this area. So it's particularly relevant to us, along with multimodal interface design and speech-based assistive technology. So thank you very much, Emily, for taking the time to chat with us. And now that we resolved our slight technology snafu in the beginning, we're ready to kick it off.
Well, hi, everybody. So I'm Emily from the University of Michigan. And you know, we do a lot of work on stress. And so if it wasn't introducing stress at the beginning of the presentation, I just don't think it would be fair with respect to our research program. And so thank you for your patience in getting this started. I'm really looking forward to talk to you about our work in effective computing, understanding how these types of technologies can be used to detect mood severity when we get out of laboratory environments. And so it's fun. I used to have to motivate why effective computing would be housed within engineering. And I used to start every presentation by saying, oh, it's part of support and entertainment interaction. But I think now increasingly we're understanding that these types of technologies are everywhere. And so now the question is, well, if we can capture and process speech easily as people go about their day, which we can't with microphones everywhere, then we can understand user need. But really, why don't we see these technologies? Why don't we have speech-based technologies everywhere that are trying to understand what users need, not just what they're doing, but how they're doing? And the reason why that we don't see more of these technologies is that speech is incredibly complicated. It doesn't just encode information about what somebody's saying, but it also encodes their emotion. It encodes information about individual differences or cultural variation. It encodes information about where they are. For example, in this room, you can hear a bit of reverberation. Often you can hear background noises such as fans or other people or animals or small children in the era of Zoom. It encodes all of this information. And so when we're trying to think about how to process speech to be able to detect signals that we care about, we really have to think not just what is our goal, but what is our goal and what might be standing in the way? How can we think about controlling aspects of the signal that might be confounding our prediction so that we could really hone in on the signals that we're hoping to measure? And so that's generally what my group is focused on. We have two main thrusts. One is multimodal emotion modeling. And here we focus on expression modeling. And I draw this point, I really want to be very clear. We're talking about perceiving how outside observers would label emotion, not an inner felt sense. And here when we're talking about emotion, we're talking about methods that involve deep learning or multitask learning or time series modeling, things that take knowledge into account, domain-related information that might tell us how best to build these algorithms. We also have a lot of energy that's focused on assistive technology. In the past, we've worked with speech from individuals with aphasia, trying to build speech recognition systems or systems that would allow us to understand severity. We've looked at mood state tracking for individuals with bipolar disorder. We've tried to estimate suicidality from natural collections of speech. And we also have ongoing work that's looking at modeling speech patterns for individuals with Huntington's and Parkinson's disease. In this presentation, I'm going to specifically talk about our work in expression modeling for emotion and mood state tracking for individuals with bipolar disorder. And I'd be happy to take questions at any point. I don't have the chat window up, but please do either feel free to actually, I'll just bring up the chat window. That way, in case there are questions, I'd be happy to discuss. Right. So First, before I get into any of this, I really like to ground the terms I'm talking about. So when we're talking about emotion, what I specifically mean in almost all cases is recognizing valence and activation, two dimensions that can be used to describe emotion. Valence describes how positive versus negative a display is. Activation, or sometimes called or often called arousal, describes a level of energy. Occasionally, one little brief interlude, I will be talking about emotion categories, but I am almost always talking about valence and activation. And the reason why we do this is that I think it's extremely important when you're thinking about emotion outside of laboratory environments to understand what you can model robustly, what you can model without needing to have huge amounts of context, without having to have a huge amount of understanding for kind of the situation that people are going through. And so valence and activation give us these models, which is why we focus on this. If I'm talking about mood, I'm talking about it clinically, and I mean things like depression or suicidality measured by clinical scales. And when I'm talking about diagnosis, which I won't really be, but if anyone asks a question, I'll be talking specifically with respect to, again, a clinical assessment of somebody's health. So when we're talking about doing these types of modeling, I generally am assuming that we're starting with some kind of audiovisual data where there also might be transcript information, either provided through human annotation or through automatic assessments, things like speech recognition. Then what we do is we extract the speech signal, and from this we have a time continuous measurement. And then from this time continuous measurement, we're interested in extracting features and then modeling the data. And in the end, what this allows us to do is come up with some time series often that in this case might be valence over time. So how positive versus how negative a display is over time. It also could be activation / arousal. It could be the probability of being in a certain category, but almost always what we're talking about is doing this time continuous prediction. All right. So first, why this area? You know, in machine learning is a wide open space. Why this area? So this area I think is so important because it gives us a chance to not just focus on what's new and what's interesting from a technology perspective, but to really feed back to society. Because anytime we have an algorithm that's performing the way we expect it to, not only do we have something new and fascinating that allows us to understand how to counteract variability or counteract noise or adapt to certain individuals, not only is it interesting algorithmically, but we have the potential to interact with science. And so that gives us a chance to move outside of the laboratory and into the real world, which kind of at a broad level is the focus of our group. Now, specifically for the work in this talk, I'm going to be talking about bipolar disorder. And for those who aren't familiar, it's a leading cause of disability worldwide. It's common, it's chronic, and it's severe. And although we use the terms mania and depression sometimes very colloquially in culture, these are anything but colloquial. And in fact, they're characterized by swings into mania and depression, where mania would have heightened energy with devastating consequences, depression, lowered energy, again, with some devastating consequences, both in terms of personal, social, and vocational effects. Now, there are some treatments that are currently available, and these treatments are pharmaceutical, which is exciting for those for whom it works. But there are a lot of people for whom pharmaceutical treatments actually are not sufficiently stabilizing with respect to their illness. Now, the other way that people often treat this is with periodic follow-up visits for monitoring. But it's a great thing that in a lot of cases, people are quite healthy. And according to our clinical collaborator, a lot of these are actually unnecessary. Now, it's great that people stay healthy, but when we start thinking about limited resources with respect to clinical care, actually having a lot of these visits might mean that other people can't get access to the care they need. The alternative way of treating this, of course, is hospitalization, which may happen after a manic or depressive episode has already occurred. But in that case, whatever devastating consequences are resulting from having an episode of mania or depression may have already happened. And so what we really want to find is a way of understanding when somebody is in need of care so we can get them the care they need before they need it. Because what we're trying to avoid is this. Is really large swings in mood severity between depression and mania. Now, I'd like to clarify, this is drawn assuming that there are no mixed episodes. Now, there often are people may experience symptoms of mania and depression, particularly in terms of how severity is assessed. But in this case, this is just a simplifying drawing. And so what we'd really like to do is, I used to say is a check engine light, but somebody in one of my classes told me it's actually a check oil light. But in any case, we would like to have a warning sign that comes up that tells us that this person's in need of care, so we can make sure that this person is then prioritized for care. Because if we can do this, our hope is to help people stabilize, is to help people stay around their baseline. And so the overarching question of this area for us is, how can we automatically identify an individual's early warning sign? From an engineering perspective, we'd really like to understand how we can control for variability. So we have technology that will function for a large number of people in many different circumstances. And that's the motivating principle behind the work that we are doing. And so this project started back in about 2012. And what we were trying to do is understand how we would be able to predict individual outcomes for rapid intervention, a project we called Priori. And what Priori actually is, what Priori is designed to do is measure people's mood severity as they go about their daily life by recording speech. And since our hypothesis is that speech will convey information not just about what someone's doing, but how they're doing, we would like to use this signal as a way of understanding if someone might be in need of care. And so we have an app that is on individual smartphones. And in fact, the only way you generally know that it's running is there's a little tiny block M in the corner that tells you that the app is on. They do have the ability, so what the app does is it records an individual's side of every single call that they make or receive, but only that individual side. And to add a little bit of extra security for that person, they do have the ability to go into the app and delete calls that they would prefer not actually be transferred to our servers. We've been told, at least from our participants, that in the majority of cases, this isn't actually what happens, but they do have this ability. I'd like to stay upfront and probably often, we take privacy extremely seriously, and we focus very heavily on making sure that when our participants have decided to trust us and honor us by giving us their data, that we're going to treat this in an extremely ethical manner. And so just if anyone has any questions about privacy at any time, I'd be more than happy to discuss this because this is extremely important to me. So when the data are recorded, they're encrypted on the fly and then uploaded to the secure server 24 hours after the calls are recorded. When they're on our servers, we extract information that includes measures such as, depending on the project, perhaps pitch or energy, other types of low-level speech features. And then our goal is to try to figure out how to build classification systems such that we'll be able to detect mood symptoms or mood symptom severity. Because then what we'd ultimately like to do is to realize that if an individual is at risk for heightened severity, we can deliver an intervention that says, you know, make sure that we are reaching out to this person. I'd like to be clear of the scope of what I'll be talking about in this presentation. It's on the measurement side, not on the intervention side. The intervention side is extremely important, but that at the moment is in future work. And so what that takes us to is two different types of calls. So we have calls that we refer to as personal calls. These are calls that are made as an individual goes about their day. The calls can be about anything, they could be talking to anyone, and we don't really have insight into the context of what's actually taking place in that call. And they're all natural speech. It's not from prompts, it's just someone talking on their cell phone. Just as a reminder, just their side of the conversation. We also have these things that we call assessment calls or clinical calls. I'll be using either of those two terms. Assessment calls are weekly labels, and that's when an individual calls into the clinical team and is assessed for the level of mania with the Young Mania Rating Scale and level of depression with the Hamilton Depression Scale. And again, these occur weekly, and they're the only calls that we have that have clinical labels. We're not deploying other types of mood assessments. We have once weekly labels that tell us someone's mood severity retrospectively over the past week. The majority of the work that I'll be talking about in this presentation is focused on the subset of our data from 60 individuals with bipolar disorder and 51 individuals with bipolar disorder and 9 healthy controls who are using Samsung Galaxy S3 and S5 phones. This subset of data includes about 50,000 calls and about 4,000 hours of speech. The full collection has about 83 participants and is up to about over 5,000 hours of speech. So we have quite a lot of data, which is very, very exciting. I'd like to pause for a second or to give people the opportunity to ask any clarifying questions about the type of data, because we're going to be using these data in most of the rest of this presentation. So if you have any questions about how it's collected or how it's labeled with respect to mood, I'd be happy to pause to see if there are any, either in chat or just asking.
Anything we should know about the people you're calling healthy controls? I mean, it's a small sample, but characteristic, demographic-wise, everything else-wise, they're more or less similar
Yes.
to the...
They're more or less similar. They have no episodes of I have to go back and look at the details to give you a more specific answer than the one I'm about to, but they don't have a psychiatric diagnosis. They have no substance use disorder. They were not age matched, which is something that I think could be really interesting to think about for the future. But at the moment, a lot of times what we're trying to think about moving towards is individuals as their own controls. We work with these people for in the order of about 6 months to a year. And so I think it's a really interesting opportunity to talk about how an individual themselves can serve as their own baseline.
Great, thanks.
Leading into a question I wanted to ask about, you may have mentioned this, and I'm not seeing it on the slide, so I may have slipped by me, is the interval of time when someone participates. Like, how long is Priori sort of installed on their device that they've sort of agreed to participate?
Yeah, it's a great question. It's on the order of about 6 months to a year, depends on the participant. And yes, so they have weekly assessments. It's every week-ish because, you know, people might have a scheduling conflict that comes up, but it's every week-ish for 6 months to a year. And luckily our participants have, I mean, this is work with the Depression Center and Melvin McInnes's group and the Proctor Bipolar team. And they have an incredible relationship with the participants, which has been really just an amazing opportunity for us.
Great, thanks.
All right, so our first attempt. So I'm gonna say, this is often the approach that engineers will take when we first enter into a domain that we think might be characterized as machine learning, where we say, okay, I've worked with acoustics in the past. My PhD was looking at emotion recognition. What if I take a similar tactic where I start with low-level acoustics and I try to recognize mood? I'm going to make the basic assumption that mood is going to consistently modulate my speech. Spoiler alert, I learned over time that doesn't work very well, but I will say that's how these projects often start, and it's of course how we did start. And so in this project, what we originally did is we took a processing pipeline that was very common in emotion recognition, where you take an audio signal, you segment the data, which is very important because we have one side of a conversation, so we actually have large amounts of silence, into regions of speech and non-speech. Then for regions that are on the order of 3 to 10 seconds, you take statistics of a feature that you might extract, in this case, speech rhythm, which was a signal-derived measure. And then from these measurements, you then classify to come up with mood. In this case, we were doing the presence of mania versus euthymic or lack thereof, or the presence of depression versus euthymia. In both cases, it was euthymia was under 6 and under on either the Hamilton on the Hamilton and Young Mania rating scale, and the level of depression was 10 and above on Hamilton depression, and mania was 10 and above on Young Mania. What we found is that didn't work at all. And we were, of course, devastated. So just for people who aren't familiar with AUC, chance is about 0.5. You can think about this as measuring, given 2 samples, what's the probability that they'll be placed in the correct order. So in the case of depression, we do see something that's statistically above chance. In the case of mania, we didn't. And we were really curious as to why, what actually happened. And this was one of our first lessons in the importance of thinking about data collection when you actually get into the wild. And what we realized is that since we had deployed this on the 2 phone types that I mentioned, the Samsung Galaxy S3 and S5, those 2 microphones were very differently calibrated. In the case of the S3s, they were overly sensitive, which meant that pressurized speech was something that would have lots of clipping, which is an irregularity that happens to the acoustic signal, where instead of having these kind of smoothly varying characteristics, it can't record the level of sound that's present in the signal, and it clips it. That means it introduces a lot of high frequency noise, which introduces a lot of error in these types of processing pipelines. What's also interesting is that when you're thinking about speech that is characterized as manic, from a manic episode, you have speech that's pressurized. And so we found that when we corrected for something that corrected for declipping, we found that we actually could have statistically significant and of course actually quite large performance gains in the case of mania. And so this was exciting and led us at the beginning to think about, well, maybe acoustic signals are really going to be our answer. But these results were only on data from clinical assessments. And that's critical because clinical assessments are interactions where a goal is to try to understand what somebody's mood severity actually is. That's the target of these things. And so when we tried to move beyond this, when we tried to move from clinical mood assessments to personal calls, we found it didn't work very well. And in fact, when we tried to move from speech rhythm to just other sets of features, we found that despite early advantages that we had by personalizing using a technique that's common in speaker verification, we weren't really able to improve any further. And we started getting frustrated because we found that clinical mood assessments was kind of tapping out in terms of performance. We couldn't really get anything on the personal calls. And so we sat back and thought, okay, what are we going to do? What are we going to do that will enable us to have more insight into what's actually happening when people are in these mood episodes, so that we can have a better way, a more robust way of actually doing these types of measurements? And so when we thought, what if we combined something that we know about mood severity, which is emotion changes, with an expertise that our group already had, which was emotion recognition. And so we decided to go back through and annotate large numbers of our calls for level of emotion. And then this allowed us to move from clinical speech to natural speech, particularly as we started to bring in speech recognition as an additional feature, not as something we looked at, but as an additional feature. And this allowed us to understand language differences, how calls differed between clinical assessments and natural speech. It allowed us to understand how we might be able to move towards predicting risk of suicide, and it allowed us to think about how we might be able to predict intervention. So what I'll be talking about in this talk, probably in an abridged way because of delicious technical difficulties, is some of the work in emotion recognition that allowed us to work in naturalistic environments, and then how we were able to use also language patterns to understand how these two domains were different. Okay. So the overarching research thread of this group, of our project, the motivation is, how can we move from recognizing mood from acoustics to recognizing mood that are focused on relevant behaviors? And so we need tools. We need new tools for this complex domain. And so what I'll be talking about are two of those tools. One is acoustic emotion recognition that's designed to work on data sets that are not purely laboratory oriented. And the other is how we can get features that describe language patterns using speech transcripts that are built on an imperfect transcription. And I'll talk about a sort of an interesting error pattern that results from this kind of imperfection. But really, our goal, our fundamental goal, is coming up with new ways, new avenues for naturalistic discovery. So why emotion? Well, emotion was our first intermediary step. And the reason why we were excited about it is that although mood prediction is challenging, it's something that's not directly observable. It's something that exists over a long time scale. And in a kind of a problematic way, emotion exists differently. Because, speech acoustics exist differently. Speech acoustics vary on the order of milliseconds. That's exactly how lexical content is conveyed. But mood varies on the order of days to weeks to months. And so what we needed is some way to bridge that temporal gap from the low varying mood information to the highly variant speech signal. And we knew that emotion can simplify mood prediction. There was some early work at Interspeech, which was one of our major speech conferences, that showed that this might be the case. Further, emotion dysregulation is a symptom of bipolar disorder. And so we wanted to try to figure out how we can design robust systems for emotion recognition that might allow us to do something really interesting for predicting mood. And this data set was annotated and described in a paper in 2018. And what we actually did is we had this pipeline. I'm going to talk about it pretty briefly. It was actually quite a large undertaking, where we started with our 60 subjects and we reconsented, because the original consent form wouldn't have allowed us to do this. So we reconsented, we talked to our subjects. And as of this paper, 12 subjects had reconsented. As of the final set, 19 had. And then we segmented the data again to remove speech and silence. And then specifically focused on segments that were on the order of 3 to 30 seconds in length. And we did this to make sure that the segments were long enough so that people could actually annotate for mood, and that the segments were short enough so that we didn't have too much mood variation. Then we inspected the segments to make sure that the individuals were actually talking on the phone and not, for example, talking to somebody else in the room, or perhaps yelling at their dog, which happened periodically. And then we annotated the data for valence and activation, where again, valence is describing the positive versus negative aspect of the emotion, and activation is describing calm versus excited. So the valence and activation annotation was done on a 9-point Likert scale with 11 annotators who are of ages 21 to 34 and native speakers of English. And they were asked to consider 2 important points. At the time, we weren't aware that we could use speech recognition as an additional source of features. And so we asked our annotators to focus only on the acoustic emotion aspect, which I realize is quite challenging to do, but it's what we asked our annotators to try. We also wanted them to focus on the subject specificity of emotion. And so we asked people to annotate a full subject's data before moving on to the next subject. Although to give aspects of privacy, we subsampled from calls and shuffled the order of the segments to make sure that people weren't just listening to an entire individual's call in order. And what we found was kind of interesting. So this led to about originally 25 and now 35 hours of annotated emotional data and across the 19 subjects. So on the right, you can see a distribution over valence and activation, where valence is on the y-axis and activation is on the x-axis. The green words of sad, angry, happy, and content are used just to kind of ground what the quadrants mean. It was done entirely in a dimensional way. And what you can notice, I think that's interesting, is just how very much is centered in the neutral region of the space, which tends to be something that you see a lot with any kind of naturalistic annotation of data. You tend to see a lot of neutral. We think of ourselves as extremely emotional producers of speech, but really we actually produce a lot of neutral content, which I think is really important to think about, but also kind of interesting when you think about really moving even outside of telephone speech, which I'll kind of highlight where we're headed later. And so you also can see region in this kind of low valence, low activation space that's associated with heightened sadness, which again, considering that we have a large amount of data that's associated with depression is something that is quite reasonable. So now all of a sudden we have annotated naturalistic data. But even though we have 35 hours of data, emotion is still a big data problem. And so we wanted to really try to figure out how we could think about transferring paralinguistic information from data sets that may have different conditions, how we can take advantage of the fact that there might be variation in different data sets and use these to build emotion recognition systems that were as robust as possible. And this is from work that it's still to appear because this journal is just quite lagged in terms of its publication framework, but it's from the IEEE Transactions of Affective Computing. And so the goal here is something called domain generalization. And the idea is building a framework that will allow you to have a classifier that doesn't just work in one space, but will work in multiple spaces by generalizing over the domains in which it's designed to function. Essentially, you can think of this as creating a middle ground representation for unseen data. So if a classification algorithm has not seen emotion data from a given speaker, it can use this kind of generalized, more robust way of describing the data so that it may be able to do a better job in the recognition. I'd like to be very upfront. None of these things are perfect. These are not solved problems, but we're looking at moving incrementally towards how we can think about using these types of data to understand how variations over the signal that we actually can measure can lead us to have more understanding about a person's own mood severity. And so, you can think about this as trying to mitigate variability in data sets that might be due to environmental noise or subject demographics or recording device quality, elicitation strategy. Some of our laboratory data sets are acted. And our goal is to try to figure out how to mitigate this so we can design emotion recognition systems that are robust enough to work in different settings. And this is, I'm going to skim kind of over this just for time, but it's essentially based on this idea of domain adversarial neural networks, which are trying to essentially unlearn domain. They're trying to come up with a representation that will no longer be able to determine if this given piece of data is from data set A or data set B. But the challenge with emotion recognition when you're unlearning things like domain is sometimes you unlearn more than just domain. You also unlearn emotion. Or you may have difficulty converging because it's not really clear what it means to not be from a data set. And so what we wanted to try to do was address these two issues, coming up with a new way of describing emotional data so that we could actually, that will actually converge and will give us a more stable target for learning. And so what we wanted to do was come up with a system that was still discriminative for emotion, something that even after doing this processing, it would still be able to detect emotion, but also has a clear target. And so the overview of this idea is that we have audio coming in, and this generates a representation. What we'd like this representation to be able to do is to classify emotion. And so for anyone who's not familiar with the term representation, it just has to do another way of thinking about it is sort of a higher dimensional or perhaps nonlinear way of taking your input features and coming up with a new way of quantifying your data that is designed to do something. So it might be classify emotion, it might be unlearned data set, it might be capture context in the case of natural language. But we'd like to take this representation and make sure that it could still classify emotion and that it is incrementally moving the representations from different data sets closer to each other. So now it is not unlearning data set, it's in fact coming up with this sort of meet in the middle approach that's moving representations from two different data sets incrementally closer to each other. And this is, again, this is from that Transactions of Affective Computing paper. So just for clarity, just for completeness, our baseline here is a convolutional neural network, a CNN. And what we do is we take input MEL filter bank data. It's frequency data that capture, essentially you can think about it as capturing, it's in line with human hearing. And so as the frequency content of these different banks increase, the challenge with human hearing, or the characteristic of human hearing, is that our ability to differentiate between these changes actually decrease. And so MFBs have increasingly wide filter banks as the frequency content goes on, so that it's sort of in line with how humans are actually processing these data. These are also common features used in speech recognition. And so the CNN is sort of our baseline system, and it was designed to recognize low, medium, and high valence. That's what the L, M, and H are: low, medium, and high. We have, I guess I should be more clear too, we have a CNN that's going to be trained on data from all data, for example, and we'll also have specialty purpose systems, or SP, that are going to be just trained on in-domain data as a comparison point. ADDOG, adversarial discriminative domain generalization, is a comparison where what we're trying to do is have our general thing that's doing the representation generation, the emotion classification in this teal color, and then the domain critic in purple. And then you can extend this to MADDOG, or multi-class ADDOG, by having multiple of these critics. And so again, you're trying to have these pairwise comparisons to make the individual pairs of data sets closer to each other, with this hope being that what you're doing is creating a more generalized representation for your data. And so the overview for the experiment that we'll run to understand the efficacy of the system is that we'll have three data sets, IE-MoCap and MSP, which are both common in the emotion recognition space, and Priori emotion, which is the annotated data I talked about in that first bit. The features are these MEL filter bank features, 40-dimensional feature vectors that are zero padded to the longest in the batch. And then our goal is to do cross-domain valence recognition in a three-class way. So low, medium, and high valence. And cross-domain is referring to training a system in one domain from one data set, testing on another. Valence, again, is representing positivity. So low, negative to positive. We have three setups, but I'll only be talking about the last one, which is training on the two laboratory data sets, IE-MoCap and MSP, and then testing on Priori emotion. And so let's look at what happened. So I'm going to ground what we have here. So what we'll be doing is we're training on all of the data from IE-MoCap and MSP, and we will be testing on Priori emotion, and we'll assume that some of Priori emotion is labeled. The amount of Priori emotion that's labeled is along the x-axis, going from 0, 200 samples, 400, all the way up to 3,200 samples. Along the y-axis is something called unweighted average recall. That's our accuracy metric. And the reason why we like to use this metric is that it allows us to account for the fact there might be distribution differences across the three classes. It's an unbiased measure. And so we take the per class recall, we can think of it as the diagonal of a confusion matrix, and take an average. That's unweighted average recall. The first thing that we'll look at is the performance with just the special, or with this general purpose CNN that's trained on IE-MoCap and MSP and just applied to Priori emotion. What you can see is that as we add data from Priori emotion, you see an improvement in performance, but it's still pretty bad. The dots here will denote statistically significantly poorer performance from MADDOG. Or sorry, just significantly different performance from MADDOG. And the bar, or the shaded in area, is representing a standard deviation of performance. So what this shows us is you can't do this. You really shouldn't do this. Please, please, please don't do this. Don't take a CNN, train it on some data, add a little bit from your domain and hope it works, because it really doesn't work very well. Then what we wanted to understand was what happens if we do something else. So in this light orange case, this is the specialty purpose system. So this is the one that's trained only on priori emotion. And what you can see reasonably is that as the amount of data from priori emotion increases, our performance also increases. What we see in this purple is an ad dog system that's trained only on either IE mocap or MSP and then applied to priori emotion. But really where we have our best performance is in this mad dog system, where we're taking advantage of all the variation that we have in our laboratory collections and then adapting it to priori emotion. And this is where we see our improvement. This is just an audio only valence model. And the reason I draw that distinction is that valence is not something that's described or is conveyed only in audio. In fact, if you want to recognize valence accuracy, it's much better to also either have text or to have facial information. And so our newer systems that are based both on facial data and based on acoustic data have performances of around 60%, which is quite a boost. But what we can do with this, which I'll probably skip just for time, but we have another paper at Interspeech 2019 that was looking at what you can actually do. And what we show is that you can use these types of measures off the shelf with Mad Dog to recognize emotion on a different phone collection for looking at the speech behaviors of individuals who are at risk for suicidality. And so just to go, I guess, very, very briefly, we have individuals who are at risk for suicidal ideation and healthy controls. We apply these same Mad Dog features and use this to, we take statistics over the segments of speech and then classify categorical labels that were measured from ecological momentary assessment. I can answer questions about this later. This is just a kind of a quick pass over it. And what we found is that if you look at the standard deviation of these measures over the individuals who are healthy controls versus those who are at risk for suicidal ideation, you actually see statistically significantly lower standard deviation across categories of guilt, hopelessness, anger at others, anger itself, and irritability. And so the reason I draw this distinction, I mean, it's a very high level, right? This paper is much longer than would be conveyed in a single slide. But the reason I bring this up is that what this is doing is using that technology that I talked about on the last few slides on a different domain to try to ask, what can we actually measure with these emotion measures? And what's kind of interesting is that, so we don't actually have valence and activation labels for these data, but we have this interesting opportunity to say, how can we use these emotion measures as feature generators that might highlight aspects of the data that we think are important or meaningful that we could then use to do a task that we might be grounded in. Something in between the low-level speech variation and the higher level, in this case, emotion variation or risk variation, and if you think about even the higher level category. And so, if you're interested, we do a lot with emotion. And in fact, a lot has come out recently. We actually, this top one was just accepted for publication literally this morning, which was exciting. It's looking at speaker level variation. It's personalized. We also are doing a way of looking at learning new emotion features by coming up with parallel corpora that are based on audiobooks and speech synthesis. But anyways, we do a lot of this stuff. So if you're interested, most of these are available on my website. And if they're not, please just contact me. So emotion's half the picture, but what if we also had language? Because as it turns out, language is highly informative with respect to how people are actually doing. And so this is from another Interspeech 2019 paper. And again, here what we get, again, we want to understand is assessment calls versus personal calls, except now instead of using acoustic emotion, we want to look at information that can be derived from what somebody's saying. And so in this case, we use speech recognition. The original priori emotion that I talked about at the very beginning was annotated, but that's just 35 hours out of the full set of data that we actually have. So here we're using an off-the-shelf CALD, which is a speech recognition toolkit, that had a word error rate of about 39%, which is, I mean, that's very high. And so we've actually switched to Microsoft. We have a very generous grant from Microsoft actually to do this, which I appreciate very much. And we've been interested in how we can use features derived from speech transcripts to understand how we can predict mood severity. Again, I want to be very, very clear. We take privacy very seriously. We are not looking at the speech transcripts, but we're using features that are derived from the speech transcripts. So essentially, you can think about the transcription of the data as yet another feature that's processed automatically by our system. And so actually, could I get a time check? I know we had a bit of a delay in terms of where we're starting. Could you let me know about how long would be good to continue?
I think maybe 5 minutes max. That'll leave you 5 minutes for questions.
Yeah, no, it's perfect. That's perfect. Okay, so I'll go over these features at a relatively high level, and we can discuss them later if there's interest. So we have features that capture linguistic style, things that deal with the complexity of speech, the syntax, looking at graph analysis, which is this really interesting technique that has been used in the past to differentiate the speech patterns of individuals in manic episodes from those diagnosed with schizophrenia. We're also looking at semantic content using a toolkit from Luke. It's a linguistic inquiry and word count. And there we're looking at various categories, things like emotions, biological processes, personal concerns, a basic lexical feature, TF-IDF, a speech intelligibility that's coming from our ASR system, the automatic speech recognition system, and also nonverbal expressions, laughter and noise. I'm going to highlight laughter. I'm going to come back to that one because there's a really interesting result that happens at the end because of our use of automatic detection of laughter. We also have speaker timing features, things that are like speaking duration, speaking rate, speaking quantity. And then what we wanted to understand is how we can model this in a linear regression context. And we use linear regression because the data set that we were working on was relatively small. And also there's a real desire to have interpretability. You can learn a lot if you actually can interpret what your models are doing and what your model thinks is important. So it's not, just as an aside, full deep learning is not always the way to go. I think oftentimes it's very interesting to think about how you can use deep learning as sort of as an input to generate features you might care about, for example, emotion or speech recognition. But then if you have these interpretable features, it's kind of nice to use them in an interpretable way. And so we're using linear regression in this context. We're ranking features for feature selection with Pearson correlation coefficient and doing a leave one subject out cross-validation. And I'll talk about this at a pretty high level for time. So what we found is that it is much easier to do this on assessment calls compared to personal calls, which fits very, very nicely with what we saw previously. But I also would like to highlight that although, obviously 0.6 is much larger than 0.3, this is one of the first times that we've shown, I think that anyone's shown, that you can take these purely unstructured data and detect anything having to do with mood severity. So we were really, really, really excited about this result. And we were also really interested to interpret what happened, because as it turns out, it's fascinating to learn about kind of what the differences are between these assessment calls and the personal calls. Because there's so many times we assume, oh, if only we have access to data that are collected in controlled settings, we can just use the patterns that we have from these controlled settings and just generalize them to somewhere else. But what we found with this analysis is that that is not probably going to work very well. So these are the sets of features that are aligned with assessment calls. They're things, if these are positively correlated features, things like the number of nouns or the total duration of the call, which has a lot to do with the structure of a clinical assessment. Because it turns out when your depression severity is higher, you talk about your symptoms for more time. And so always be careful of features like duration or segment count or short utterance count. Those features tend to be very, very, very tied to the structure of a clinical interaction. Also assent. As it turns out, when you have questions that could be potentially answered with yes and no, you have a lot of yes/no features that occur in your call. There are also features that tend to correlate that are negatively correlated with depression severity. I think leisure is kind of an interesting one. But what's interesting is those features don't work well in general for personal calls whatsoever. And in fact, the features that work well for personal calls are quite different from the ones that work well for assessment calls. In fact, things like negative emotion, which, that is an intuitive finding, but there's something to be said for an automatic system that results in something that's actually intuitive. The presence of negative emotion tends to be more strongly correlated with depression severity. The presence of anger, the presence of anxiety, the presence of discussions about death, noise, which we think has to do with sighing, ASR confidence, the standard deviation. So there's more variability in the ASR confidence. Also the number of pauses per second, there's more pausing. And these are within the segments, not considering the segmented out silence. There are also features that are negatively correlated, so it's harder to do speech recognition when depression severity increases. The speech characteristics are changing. But also what we notice is these features generally don't work well for assessment calls. And so it's really, really important to think about the context of these measurements, because the context is going to really influence the type of features that either have meaning or don't. Really briefly though, I want to highlight laughter because that one's a weird one. So we found that the amount of laughter is positively correlated with depression severity, which is a non-intuitive finding. And so we went back to our data and tried to understand why. And luckily, as I mentioned a few times at this point, we had some of our data were annotated. There were some of our data we were allowed to listen to. This was not laughter. This is the classifier being incorrect. It was crying. And so it also points out the interesting aspect that comes from doing automated analyses, but also the interesting possibilities of using systems that may not be perfect in their classification, but in their error may have really interesting signal. And it becomes particularly of note when you think about long-term, longitudinal, personalized measurements, where if you understand how an individual is orbiting about these features, then the exact point in a space might not matter as much as their variation within that space. So with individualized systematic performance, I think you can really do interesting things. And so we can robustly detect emotion. We can measure patterns in language and relate them to depression severity. What's next? Well, what's next is trying to figure out how to get more context. So I'm going to go over this part very quickly because I know that we're pretty much done. So we're trying to understand how language can be context. We want to try to understand, given telephone calls, for example, what is someone trying to accomplish? Because if we can understand their communicative goals, we're going to be able to have mood severity algorithms that are more targeted to how mood actually might be manifesting. As my collaborator Melvin McGinnis likes to point out, if someone is ordering a pizza or talking to their boss, they're probably not expressing their mood in the same way that they would be towards a confidant when they're self-disclosing. So if we can understand what the linguistic information is telling us about the context of these calls, we can have more targeted mood assessments. We're also moving even further into the natural environment. Right now, I'm talking about telephone speech. In the future, I'm not. I'm talking about using ambient recording. And so we're trying to understand how we can design robust emotion recognition systems that will be robust to naturally occurring noise sources. Understanding how we can mitigate the effects of noise that we can reasonably expect to occur in our environments. Understanding how we can learn timelines that might tell us a little bit more about how variations in energy over time might be associated with early warning signs for example, a manic episode. Learning personalized distributions, because if we can have a better understanding for how someone's personal characteristics vary, then we might be able to use these patterns in emotion to understand how mood episodes trigger changes in emotion expression patterns. And then when you're talking about data in naturalistic environments, privacy has to be a component. And so we're trying to understand how we can use these ambient pipelines, but add additional security. Things like on-device functionality and new algorithms that are designed specifically to have privacy-preserving transformations so that our participants can have more assurance that the information that they're measuring will not be leaked to adversaries. So, in conclusion, mood recognition is promising but challenging. I think there's a lot of potential in doing this, but it's important to do it extremely carefully. We can detect measures of emotion and mood in clinical calls, and we can estimate emotion from naturalistic contexts. The ratings of emotion are related to both clinical and personal conversational data, but future work absolutely has to focus on mitigating the variability in the modeling process. But I think the future is bright, as long as we are concerned with ethics, because oh my goodness, we have to be concerned with ethics. When we think about doing these types of automatic quantifications, when we think about doing these types of measurements, we have to think about the implications of how these systems could be used and the effects on our participants. But fundamentally, as an engineer, I also think it's really an interesting opportunity to embrace complexity, because speech tells us so very much about not just what someone's doing, but how they're doing. And so this is the motivating idea of our work. And so with that, thanks for your attention. I'd be happy to take any questions.
Emily, thank you very much. That was terrific. So I'll be brief here. Questions, folks? We have just a couple of minutes left.
Yeah, I have a quick one. So this is Trevor Cohen here. Thanks for a great talk. I wanted to ask, in the differences between the clinical and personal calls, did you look at all at the pronoun characteristics that come out of Luke?
Yes,
like in a sense that one of the
yeah, let me see if I have that in backup slides. Usually I'd be able to just go in directly, but I think that's one of the backup slides. Give me 1 second to see if I can find it. But yes, there's a pronoun differences. For example, the use of I was higher when individuals were depressed. I'm not sure if I have this here, but yes, we did find that as a feature. Let's see.
You know, I was curious if that was a feature that differed between the two call types, because Pennebaker would have us believe that it's, you know, our pronoun use is subconscious, right? So it might not vary depending on the purpose of a call as much as some of the other features.
Yeah, absolutely. And one of the other things that we've been looking at more recently, which I'm not talking about because it's very, very much work in progress, but is thinking about even specific types of pronouns. And so we've been interested in the phenomenon of a generic you, which is, so specific you would be, I'm talking specifically to you, generic you would be, one reaps what one sows, you reap what you sow is the generic version of that pronoun. But it tends to be used a lot in resonance and meaning making. And so we've been trying to think about how even the type of pronoun that someone's using unconsciously might also play into their expression of mood. But yeah, I can't find the backup slide, but yes, we did find that I, for example, occurred more in when individuals were depressed.
Thanks.
Emily, fascinating work. Thank you so much for taking time to present to us. And I'm sure some folks may follow up with outreach about questions or maybe engagement in some projects that are percolating on our site, which I think would be right up your alley. So hopefully we can keep the conversation going.
That sounds wonderful. I look forward to it.